In this video, I will be explaining to you how quantum mechanics replace classical ideas of physics. My name is Wani. I'm a philosophy student at La Sorbonne. Here, I'm sharing with you my notes that I took for my class on the philosophy of physics. And in this video, we'll be focusing on the study of matter at an atomic scale, how it is that there were 5 stages, Bohr's atomic model, I do not know how to pronounce his name, the Broglie, and the wave-particle duality of matter. Then we have Heisenberg's matrix mechanics, Schrödinger's wave mechanics, and then von Neumann and the mathematical foundations of quantum mechanics. So the first one that we have is Bohr's atomic model, quantized energy levels. So this is an extension of Planck's quantization of energy exchange. So that is in my first video, which is where I talk about how it is that we arrive at the fact that we believe that light moves both as a particle and as a wave. So if you're interested, I will put it in the description below. But basically, he's taking the idea of quanta and he is making it apply into a different observation. So to explain why electrons remain stable around the nucleus instead of collapsing into it, Bohr proposed that electrons can exist only in certain allowed discrete orbits around the nucleus. So when we say discrete, it basically just means discontinuous. Continuous means that, something happens and then you're following it. And then you're like, okay, it's a continuous observation or a continuous measurement. However, when we say discontinuous, it just means that you're observing and where'd it go? It's discrete, so it's hidden. You can't see it, it's discontinuous. The idea about that, I think, can be explored if I add something about Schrödinger and how it is that he talks about the illusion of the perfect picture, as in we have every single measurement. He shows that how even in math, how it is that you have, I think it's called the diactic and the triactic fractions, and once you mate them together and make a periodic bitriactic function, you still don't actually get to measure every point. So it's just showing that we're actually not capable of creating this picture. So coming back to Bohr's atomic model, this basically is an extension of the idea of quanta, the idea that light is emitted in packets. But this idea of quanta is actually about quantum jumps. So electrons do not change energy continuously, but move from one energy level through sudden transitions called quantum jumps. Oh, I actually made a video on this. It was my assignment or my paper on What is Life by Schrödinger, and he talks about, the analogy of quantum jumps with mutation, but quantum jumps are actually more mathematically well described than mutation. Biology is probably the most difficult science to actually be able to come up with a description because it's so dynamic. I spoke to a virologist when I was in Hamburg and he said that the interesting thing, I reformulated, and what he was saying was just is it what's interesting to you is the fact that how can one virus work against so many different kinds of bodily compositions. So why some people are immune to certain viruses and some people aren't immune to certain viruses. What is the common elements between all these very different biological makeups that makes it so that a virus can or cannot thrive in one of the systems? So with that parenthèse aside, let's go to number 2, which is the Broglie. Someone maybe can help me with the pronunciation, and the wave-particle duality of matter. So this is also another form of extension. So in 1923, the Broglie extended principle of the wave-particle duality to all particles. So this includes electrons and atoms. So even matter has wave-like behavior. So matter. Does anyone have a description of matter? It's so funny because I made this video when I was taking a class on Berkeley, and then I was like, is this a precursor to quantum mechanics? And then now you can't talk about matter without talking about Berkeley. Yeah, and also I did a class on materialism. I would refer you to that video to see how troublesome it is to talk about what matter means. But based on this, I'm assuming that matter just means that it's everything that has a physical concrete existence. But continuing on, every particle associated with wavelength determined by its mass and velocity. I guess that's the definition of matter. Hypothesis confirmed that through electron diffraction experiments. 1999 shows quantum phenomena of wave-particle duality not restricted to the microscopic system or individual atoms. So it's not just about like the small micro scale, but essentially it's the idea that like, you know, how it is that whatever we observe or whatever we use to explain like the very small seems to also apply to the very big. So I'm assuming here when we say matter, it's just about the very big or like more complex systems than just like the very small isolated system or something that is just individual. The example was large molecules like C30 fullerene, which I don't know what that is. Basically, it's a molecule with about 60 atoms, can produce wave phenomena, which includes interference and diffraction. So let's go to number 3, which is Heisenberg's matrix mechanics. Matrix mechanics is one of the first foundations of quantum mechanics from 1925. It describes quantum systems using abstract mathematical objects called matrices. It's not matrix with the X, it's with the CE. Matrice. I'm just going to pronounce it in French because I don't know what it would pronounce like in English. So called matrice, without relying on classical concepts such as electron orbits or trajectories, which cannot be directly observed. Physics now does not aim to determine the exact position of the electron, but it focuses on the relationship between measurable quantum states and observable energy values. This is a shift away from intuitive visual models towards a theory based on directly measurable quantities. So this is like really interesting because like, again, I have to make a video about it, I think. But it's just the idea that like, you know, how is it that can you even say that this particle is the particle from before? There was this one part that I noted in that paper or that section of like Schrödinger's book. I was just like, so you're telling me that any identity of any object is just based on like us guessing or believing in this historical path that we're not even sure? Like, how do I, okay, if I'm like, this is particle A at 1 second, this is particle A at 2 seconds. How do I know that this is not particle D at this 2 second point is the question. How can you guess this identity based on this path that you have no actual guarantee that I know of, this is my understanding, of how it is that it moved from here to here. I'll put like a screenshot here from like one of my class notes just so that you can see the difference. Basically, like we're removing this idea of like this privileged referential point, which is like that 0 that you see in the middle. And we're measuring based on intervals between like 2 different particles positions. So that one we claim to be able to measure because it's again like, you know, this is exactly the screenshot of whatever it is that you have at that time. These are exactly where you know where the particles are at this isolated point after the wave collapse, depending on what depending on what interpretation you go on. But that one we can actually measure because we have that, you know, in that instantaneous capture. And now, like, you know, I'm risking saying nonsense, so I'm going to stop. But the idea here is that instead of assuming that we know that this is the actual path of the trajectory of a particle, we at any state, whatever it is that we have exactly, we measure these things without like this gap of 1 second, 2 seconds. So the next one that we have is Schrödinger's wave mechanics in 1926. So this is where Schrödinger introduced his equation. The equation, as we will see when I talk about like the measurement problem, is the thing that gives us all the information that we need of the particle at any given moment. And it is deterministic because if a particle follows in this equation, it means that there is only one value that you could ever end up with. So it's deterministic in terms that you come to one unique value. The consequence of this is that electrons do not possess a precise trajectory, but quantum mechanics predicts a probability distribution describing where the electron is likely to be found. When you put in this initial conditions, if you follow the Schrödinger's equation, you will have one unique set of probabilities. When we say that it's deterministic but probabilistic, it means that the result of its probability is one set and not multiple different measurements of probability. If this is not clear, write it in the comments and someone should be able to answer you if it's not me. The last one is von Neumann and the mathematical foundations of quantum mechanics in 1932. Von Neumann is also the person who introduced the wave collapse in the orthodox version, which we will talk about. but he's the one who unified Heisenberg's and Schrödinger's approach into a single mathematical framework. And this is where physical quantities no longer is represented by ordinary numbers, but operators acting on quantum states. So the formalization led to the axiomization of quantum mechanics. So what this truly means, I cannot tell you. I have in my mind what I think it means, but instead of giving you wrong information, at least you just now know that who's the person who created the formalization of quantum mechanics. It's von Neumann. And yeah, I hope this was helpful to you. And the next video, I'll be talking about the debates on the foundations of quantum mechanics. So how it is that, what it is that I told you about the Copenhagen interpretation, which is non-deterministic but a complete theory, and the opposite being the deterministic approach, which is an incomplete theory. And why is it like, why is it deterministic but incomplete? Find out in the next video. I hope this was helpful, and I'll talk to you soon.